Podcast is now starting. All attendees are in listen-only mode.
Hello and welcome to this webinar. I suggest we wait 2 more minutes as people are coming in and then we can start. So hello everybody and thank you for joining this webinar on steel design. My name is Iveta Georgieva. I'm a product manager working with steel design and also other things in SCIA Engineer. So this is a two-session webinar. So today is part 1 where we will design a steel hull. So the idea is that you can ask questions during the webinar via the chat screen. I think that maybe we already have some questions coming in. Also feel free to give suggestions what you want to see in part 2. So what I will do today is I will design a steel hull in one way, and then next time I will design it in another way. And then we will see what the differences are. So first I want to start with my presentation, a little bit show you what is possible in SCIA Engineer related to steel design according to Eurocode 3. This is for people with very little experience in SCIA Engineer. So what we have is checks according to Eurocode 3, ULS and SLS checks and design of members that can be prismatic members or members with variable height. Members can be curved, straight, and that's related to, let's say, the ambient conditions, the standard checks. We also offer fire design and design of connections, but these are not the topic of today's webinar. So today we will mostly be looking at the ULS design of the frame, and if we have some time I will also show you the SLS. If not, that I will move that also to the second part, which will be planned in the next few weeks. So on the level of ULS, we always have section checks and stability checks, and I will talk about these two separately. I have SCIA Engineer open, and I already have prepared a model. Because we don't have a lot of time today, I don't want to bother you with the modeling. So I've modeled a 3D hull, and the geometry of it is, let's say, a little bit irregular. That's really not a problem. So it's not exactly a rectangular building. We have two spans, two holes glued to each other. And what I've done is I've modeled the 1D members, I have connected them, and I have used a few important features, and I will explain them now. Related to supports, all the columns I have supported with, let's say, rigid connections along the strong axis of the member. So here we can extrude the member, and we will see that we have a rigid connection in this direction and a hinge connection out of plane. And this type of support I have applied on all my columns. I have also introduced hinges on my structure. So here you can see that all the secondary members have hinges on both of their ends. And I've also used another functionality which has some benefits. This is the so-called axial force only. So if I set my bracing, for example, as axial force only, then I make sure that these elements will only be taking normal forces. So either tension or compression. If we look at the internal forces of our structure, let's show them for the whole structure. We see that these elements have normal force, but bending moment and shear force they do not have. Sometimes this element cannot be used, and that's usually the case where you have internal nodes. If you have axial force only element and you have internal nodes, which means that some other elements are connected to it, you will get singularities in your structure. So what you can do is, for example, I've done it here for this brace. You can just define hinges on this element on both sides, and the effect will be more or less the same. So the next thing I want to show for the ones who have, especially for the ones who have little experience with SCIA Engineer, is a cross-section library. So I've selected a few cross-sections. I've also used the, let's say, first show you the view parameters. In the view parameters, I am using color by cross-section, which means that I see all the different cross-sections that are used in my model. They're in different colors. And here in the library of cross-sections, I see these cross-sections. So for the ones of you who have experience with other software, it's important to understand that the cross-section instances of SCIA Engineer are sort of design groups, which means that if you assign the same cross-section to a member, so for example, I will select this one, then I will select all the other ones that have this cross-section. It means that these members will always be optimized together. If I would like to not have it like this, what I can do is I can simply define a new cross-section for these columns. So let's say I copy this one. I just copy it. It's now here. I just select the two columns and then I assign another section, and now these sections will be optimized separately from the rest. So cross sections are sort of design groups, automated design groups that helps us to make the design more reasonable. The next thing that I wanted to show you is something that many users don't know about. That's the possibility to model a member which is defined not by a straight line but by a polyline. So here, if you see this element B10 is actually one single element, and you can do that. I will show you how to do it, but first I will tell you why this is important. So if you, for example, are going to check the stability of this member and you want to consider this as one span supported on these two columns here and here, then it is good to model this as a polyline. And there are no limitations on coming from the fact that you have modeled it like this. So for example, let's say I want to model a member. I can just use this option, which is the straight line, or I can define a member which is continuous like this. And I think one of the most important differences is that in the so-called buckling settings, which I will be explaining today, we can consider this member as one entity which has, for example, a span which is supported here and here, and then here this part is a cantilever, etc. So I've used this nice functionality to model my main girders. So I will just undo and delete these members. Another thing I've used is the haunch functionality. So the haunch functionality allows us to manage a member with a haunch in a more simpler way. So I have defined a haunch on this 1D member. And now if I optimize the section, it will automatically change the part which is prismatic and the part which is inside the haunch. And it will not, I don't have to separately design these two parts and then make sure that they are let's say, compatible at the end. So the haunch and the arbitrary profiles, that's what these, let's say, components do to members to allow us to easily design this kind of members. So after I have modeled this structure, I have also connected it. So normally connection is always something that you should do as you're modeling, during the modeling, or especially at the end when you are finished. So you connect all of your members to make sure that everything is connected. So for example, in SCIA Engineer, you don't have to model a beam every time. You don't have to split a beam every time something frames into this beam. You just can draw a straight line from here to here, or in fact, this is this polyline. And then SCIA Engineer will understand that this is a member here which is framing into this one, and will create internal nodes for you. So this happens with the connect function. And then another thing that is good to do before we run calculation is to check structure. So this thing also does, let's say, good things on your model. It checks whether you have elements with zero length, whether you have duplicated, like for example, you've modeled two elements on top of each other, whether you have invalid data, etc., or the same name used twice, and so on. So it's good to run this after you finish the modeling. So for example, here you see I have two nodes on top of each other. This is fixed, and now my model is okay. I have in fact already calculated the model previously, and I use this function result locking, so I can store my result just so that I can show you something without having to calculate. But in fact, this is linear calculation, goes quite fast, so I can just run the calculation. And then as the calculation is performed, what is the most important thing that we have to do after we finish modeling, in my opinion, is to check the deformation. So we are looking whether everything is well connected, whether things are not going all over the place. And for me, the best way to do that is if we go to results. There are various ways to do it, but I think that the nicest one is going to 3D displacement and using this option wireframe. So wireframe suppresses the generation of pretty images of a 3D displacement, and it just shows us a deformed shape. Let's show self-weight, and then we refresh, and then we obtain, in fact, the results. So here, I think it's important to do ourselves a favor and turn off the so-called system line. So this we can do via the view parameter settings. We turn off the system line, and now we see a nice deformed shape. And we can inspect whether everything is good. Here under the view settings, you also have the option to use an animation window. So when we run the animation, we can see, does this make sense? Is this structure deforming in a reasonable way when loaded under self-weight? So we see this and we say, okay, now everything is connected. It makes sense. Then we can proceed to the design. I also want to show you the loads that I have defined on the structure. So here I will restore my system line. The loads that I have modeled on the structure, so automatically I have self-weight calculated by the software. Another thing I have done is I've used a 3D wind load generator. And I know normally when people are working with a structure that is not fully according to what is described in the Eurocode, if there are certain bends and twists here and there, they always have a lot of problem to define the wind. I have used a trick here that I would like to show you, and feel free to send me your comments and whether you think this is a nice trick. So what I've done is, because my structure is more or less regular, in fact, it's close to a rectangular shape, and the roof is not so different from a dual pitch roof. What I have done is I have modeled load panels around my structure. And the nice thing about load panels is that they distribute load not by contact to your elements. So it means that even though the element is located here, this load panel is able to distribute load to it. And there is a function here which is called maximum eccentricity of members. So this allows you to set how much eccentric should a member be in order for it to take load from the load panel. If you want to inspect also how the load is applied to members, there's this option under the view parameters. This is on the first tab, panel display linked members. When you show that, you see this big green line which says in this place I have detected a load bearing element. And also I here have this so-called tributary areas. When I select this tributary area, I can see this tributary area is carried by element B12, which is this column. And the same goes also for the roof, which is a little bit irregular. When we look at the load panel, it's the load bearing elements are at an angle to its load bearing direction. This is also not a problem. We can control this by another parameter in the load panel. And this is the so-called maximum angle for transfer. And in this way, we are able to apply the load from, let's say, rectangular envelope of the building to the structure. And in this case, I've made the assumption, of course, this is always to the discretion of the engineer, to assume that this is a dual pitch roof. Also, of course, you can make other assumptions. What this delivers as a result, so I've created 4 load cases from wind. In fact, I had more, but I've deleted the ones that had lower loading. The 3D wind load generator, for the ones that don't know where it is located here. You can create your load cases from this button, and then here you run the generator, and then it makes the calculation and it applies the load. What I want to show here is more or less what zones I've obtained from this approximation. So if we look at, let's say, wind from opposite of the x direction. So here you see zone D. Here is, these are these little letters here that this is zone A and B. They're just behind. Wait, I will just do this. Zone A, zone B, zone C. And the same on the other side, zone A, B, C. And then on the roof, I have here the zone F and zone D and etc. So I think this is something that I used in order to avoid the fact of having too many problems with load panels that are, let's say, at an angle to each other, which means that by default, they will be considered as separate walls, which means when I have wind on this direction, I would have, so wind from this direction, I think it's 90. I would have had, so the zones A, B, and C, I would also get them here like A, B, and C because this is not a straight wall. So the load panels I also reused in order to define my snow load. So here the snow load I've applied directly on this panel. It's this 0.8. And I've added the load coming from the snow accumulation via another nice function, which is the free load, which allows me to apply a load in a range of Z values in this case. So from 5.8 meters, so here 5.8 to 7.5, I am applying this load of snow accumulation. And the same for the permanent load, I have applied it directly on the load panel. So these are my loads. And automatically by SCIA Engineer, I have generated combinations which always get updated whenever I add more load cases to my model. I have, in the case of a steel structure, set B ULS combination and SLS combination. This is a characteristic one. But may I use linear analysis to design this steel hull? And for that, I will go back to my presentation and we will discuss that. So this I've taken from the Eurocode, what Eurocode prescribes in chapter 5 related to structural analysis. So in fact, they say, how do we take into account second order effects and imperfections which exist in every structure? There are 3 ways, both by the global analysis. So it means both, they mean the second order effects and imperfections, or partially by the global analysis, partially through individual checks according to chapter 6. And the third method is individual stability checks of equivalent members. That's important, equivalent members according to chapter 6 with appropriate buckling lengths. So I've called these plan A, plan B, plan C. And today I want to focus on plan C. And this is because I find that this is the most preferred method in the design of steel structures. But I would like to discuss a little bit how we should do it in a correct way. So in fact, when we are using plan C, we are using the equivalent column method, which means that we are taking our member, which has a certain cross-section and internal forces. But in the checks that we will do according to chapter 6, we will assume that this member has a different length than its actual length, whether longer or shorter. So that's the whole logic of this method. And if you look here, I've taken this flowchart from a publication called Semicomp Plus, made by the same committee that publishes the Eurocode 3. And so what they have published in this little, let's say, booklet is a flowchart which explains what we have to do. So in fact, plan C fits in these two columns. So in fact, they say if you have a non-sway frame, then you can do first order analysis. You don't have to account for second order effects. You don't have to account for imperfections. You can just do checks. If you have a sway frame, you may do one first order analysis. Then you have to use the buckling length method. You don't have to do any of this. And then you can do stability checks with the sway buckling length. But I need to clarify that, in fact, using buckling lengths doesn't mean to use these buckling lengths that we know from like just engineering literature. In fact, these buckling lengths, they are valid, they are correct, but only for non-sway structures. So in fact, if we have here this frame and we say this is a non-sway frame, and here we have stiffness equal to infinity, this non-sway frame, in fact, yes, indeed, here the buckling length is 0.7 of the system length. If we have zero stiffness, then here we have a cantilever, then the factor is 2. If we are somewhere in between, we don't know directly what is the buckling factor. We can do the same exercise if we have hinges here. If we have hinges, then here this mu becomes 1, and then here we have a mechanism, and then here also mu may be bigger than 2, it can be 3 or 4. But the most important information here is that if we do plan C with linear analysis, we need to determine alpha critical and we need to determine our buckling lengths. If we do second order analysis, we don't have to do that. And this is a topic for the next webinar. So the Eurocode defines alpha critical. So in fact, it tells us when can we ignore the increase of internal forces that are caused by the deformation of the structure. And then they say alpha critical bigger than 10 for elastic analysis. If we use plastic hinges, then it's 15. In our case, we will not use plastic hinges, so we will stick to this criteria. So if we read this carefully, we will see that alpha critical is in fact the buckling factor or the critical load factor that we obtain from stability analysis. Here you see if we multiply the design load, so the ULS load on the structure, with this factor, we will obtain the critical buckling load for global instability based on initial stiffness. Okay, so one last comment on this one is to not mistake the sway and non-sway classification with braced and not braced. Here I found just some screenshots from the internet, some articles about it. If you have a braced frame, it can also have sway deformation. And in the past, there used to be this criterion to say whether your structure is non-sway when it is braced. They would say if your deformation without the brace is reduced 5 times by your brace, it means that you are now in a non-sway situation. But this is This is very arbitrary, and it's today questioned by many people and saying, why is it 5? Why is it not 10 or maybe 8? It is completely not scientific, and it's also very difficult to use. Every time to remove the braces and see how much the deformation is changed. So generally, I think that the alpha critical method is more easy to apply. So I will now show you the section checks. So section checks are the first part of our ULS control. And they are just checking whether you have enough material inside every location on your structure to capture the internal forces inside this location. So if we have failing section checks, what we can do, we can increase the cross sections. Sometimes changing hinges, supports also can help us with section checks, but we always have to make sure that whenever we change, we add hinges or we change supports, that corresponds with the connections that we will put on site in that structure. Also, the loads, of course, influence the section checks, but these are more or less defined by the code. And also the analysis type. Generally, it's considered that in second order analysis, we will have, for example, bigger moments because we have bigger eccentricities, imperfections, and second order effects. Stability checks. I've added, so in my initial flowchart here, I've added this part. It's a little bit more wiggly. It's the determination of buckling lengths because it's not always 100% clear. In fact, SCIA offers an automatic calculation of buckling ratios, but there are some limitations, and we will talk in detail about what these limitations are. And also, whenever we face these limitations, we can always calculate our buckling ratios from stability analysis. This is also relatively automated inside SCIA Engineer, and it is easy to do, and I will show you how to do it today. So first, I want to come back to my model, and I want to show you, I think I've lost my results, so I will run the calculation. So I want to show you the steel menu for the ones of you who do not have a lot of experience, at least in steel design and SCIA Engineer. I want to show you more or less how the structure is, let's say, organized. So if we go to the steel menu, we will see here many items, and practically everything above here are settings and everything below here are results. So we start with the general setup, which we are not going to discuss the settings in detail today. But if you change something in this setup, it applies to the whole structure. These settings I will go through in a few minutes. They apply to, in fact, to groups of members. And all the other settings are members settings, which means that if I apply them, for example, I can apply stiffeners to a certain member, which will help the shear buckling resistance of a member. I can also add sheeting, which will increase the stiffness of my member when I run the stability checks. This is related to cold form steel members only, and this is related to battened members only. So we will not discuss these today. So I would like to, let me go activity by layer, restore my structure. So beyond the settings, we have, let me disable this one. I think it's in the wrong layer. So I will remove it from the selection. Okay. So when we want to run the checks, here we see the ULS checks and the SLS checks. We then see the property of these checks, and we have a few important elements here. So first of all, the selection. Do we want to run this check for all members of the structure or for certain members of the structure? There are some filtering options. Then we can select, let's say, the load case or combination for which we want to run the checks. And then we want to select what are we showing. So I will just run the check. And we will see now we have lots of problems in this structure. I randomly selected the cross sections, so we see here we have some members buckling, etc. If we want to get a better understanding about our structure, it is always good to first look at the section checks and have an idea of where we have problems on the level of section checks. And so here, in fact, it's just a parameter that we can select from the list here. And we see that, in fact, we have some problems with the cross sections of the columns, that they cannot take the internal forces in our structure. Something else I wanted to show the report. So I maybe switch back to the overall check. So I like to use table results. So I think it is, I pinned it here. Okay, I like to use table results whenever I am working with the whole structure. So everything we see in the 3D window is also available in table results here. So if I want to see, let's say, a check for each member of this structure, I can refresh that, and then I obtain this in my table results window. So here we can select, for example, this purlin, and we would like to see what is wrong with it. So usually 999 in the steel code check means that there is an error message of some sort. So we see the section check is okay, but we have a very large, let's say, lateral torsional buckling, and the combined check is failing. And we can go and see the detailed output. And then here, in fact, we see a more detailed calculation of the of what's happening in the structure. There is also the possibility to, I will show you, to see formulas. In fact, here in the settings of the detailed output, there is the possibility to see formulas, tables, or both of them. So let's say I would like to refresh the output and see the formulas instead. And so here we see the standard compression check, bending check with the safety factor, and etc. Quite familiar from our classes in steel design for everybody. So we see the combined check, and then we go to the stability checks. So here we have the derivation of buckling factor, in fact, critical loads, slenderness, and then in the end, after all the calculations, we see the check. In the case of torsional flexural buckling, we are checking also like the torsional instability. And then in the case of lateral torsional buckling, we start with the calculation of M critical, and then we apply the check. And then more or less the more complicated check, not in this case because this is an asymmetrical section, I will show you maybe for an I section later on. But then we also have the bending and compression check. And then here, let me see what the problem is. I think that probably the critical load is lower than the force applied on the member. Let me see if there is a, yeah. Here it's also shown as a warning directly on the member. It says the compression force exceeds one of the critical loads. So that's usually should not happen. So that's more or less how the report works and how table results works. Another nice thing that we find here inside the check dialog is the AutoDesign itself. And so this AutoDesign, when you run it from here, works section by section. So in fact, I normally should use this filter on cross section, and then I can go one by one and change the cross section. So in this case, I just press search for optimum, and it will find a better section that fulfills the checks for this member. And then I need to do that for all of the members separately, but I will show you later on that it's possible to do it also in a batch for all the members at the same time. So in fact, if we go through all of these, we can optimize the structure. So I've also obtained often the question, people who want to do pre-design of their structure, and they would like to optimize their structure based on section checks only. And in fact, although it's possible to show the section checks on the structure, if I would like to run AutoDesign with section checks alone, I will get a message that so here, if I run AutoDesign, it will say the value will be switched to the first one. In fact, it's a very confusing message, but it says that this field will be switched back to the overall check. So this is done in order to prevent errors for inexperienced users that they are running AutoDesign on section checks alone. Which can be dangerous. But of course, there are people who want to just get an initial idea of, they don't want to deal with backlinking settings. They just want to have like a minimum idea of how much steel they need for a project and then apply maybe 30% extra just to give a quote. There is a way to do that, and this is a very nice opportunity for me to show you the steel member data. So in the steel member data, there is this option which is called verify section checks only. If you switch that to yes, then you can apply it to, in fact, I think I've applied it only to one member. Well, no, I've applied it to one member, so I will delete it. Excuse me for the error. So I will apply this when nothing is selected, then I will select all, and then I will apply this data to the model. Usually this option is very suitable when you are designing your bracing, but I will, just for the purpose of demonstration, also use it on the whole structure. And so in this case, when I perform section checks only by member data, then I'm able to auto-design my structure. And I've even prepared a model here. I'm not going to go through one by one the sections to optimize them. But the whole idea here is that it is possible to just use the section checks to run AutoDesign if you use member data on your members. So in fact, so this is the structure after I have optimized it. And now I want to show you something. So in fact, this is not the reasonable design. It's only just based on the section checks. But I want to show you the effect of tension-only bracing. So normally bracing, especially when it is slender, and it is usually slender, is designed to not take compression forces. And because we want it to only take tension forces, we need to run, in this case, nonlinear analysis. So I will show you how to do that. So I will again activate result locking to not have to recalculate. I will go to structure, and then I will apply model data to my bracing. So under model data, I have this property called beam nonlinearity. So here, if I select all my wall bracing and I apply beam nonlinearity, here you see I have various kinds of nonlinearity. I will use the tension only. And then you see these little labels appearing on the members which have this nonlinearity now. Then I will select the roof bracing, so these members, and I will apply beam nonlinearity tension only. But this is not enough in order to take the tension only behavior into account. What we need to do is define nonlinear combinations, because this element requires nonlinear combinations in order for it to be calculated correctly. If you just run linear analysis now, this will not change your results. Nonlinear combinations, there are a few ways to generate them, because here normally automatically it just asks you to create something from scratch, but that's not the most smart way to create nonlinear combinations. A way that I like to do it, and it's not the only way, is imagine that we have now our steel code check run for the structure, and we can extract the critical combi key. So here there's this option, new combination from combi key. So in fact, what this is doing is for every element, it's looking what was the most dangerous combination key from the ones that are generated from the code-based combinations. And it lists them here. And here I have to go, unfortunately, one by one. There is no select all. Or I can select some of them if I think that some of them may be relevant. And then here, from here, I can create either nonlinear combinations or stability combinations. And I can give them some sort of name. I'm using them to show the tension only. And then I immediately have 15 nonlinear combinations already created. If we go to the nonlinear combinations menu, we see those combinations there. We also have a result class which contains these combinations. So now I will run the analysis. And I want to point out that although these are nonlinear combinations, that doesn't mean that we are running second order analysis, and certainly not with initial imperfections. What we are doing now is we are just taking into account the effect of the bracing on the model. And you can even see it here. There are not really like a sophisticated Newton-Raphson analysis with stepwise application of the load. We have a portion of the load which is applied in the beginning, if you can see it here. And then the full load is applied on the rest of the structure that does not have compression diagonals, let's say. And so in fact, we still are running first order analysis. And this is why it's also like the calculation of these combinations doesn't really take so much time. And now, just for the purpose of demonstration, I will show you that there are changes. Now, if we run the class of nonlinear combinations and we check what is happening with the structure, we will see that although the structure was optimized for the linear combination based on the code, for the nonlinear combinations, we have some elements failing. And in this model, it's not very pronounced, but sometimes these differences can be big. And here I made just this, I just copy pasted the values of the unity check in this table to show you that it's not just the braces that get different forces, but also the columns and some other elements may get slightly different internal forces because of the exclusion of the tension diagonals. So in fact, for the purpose of demonstration, I will continue using the linear analysis, but be aware that it is always healthy to have these nonlinear combinations and to optimize the structure based on them. I will look into my cheat sheet to see what I have, if I have missed something. So I think here I need to remove the, so I had here the steel member data. And what I like to do is I like to use this member data on the bracing. So I'm not going to remove it because I will continue to work with the linear analysis for, let's say, when I'm just quickly running analysis to check what is happening with the structure when I change certain settings. And when I use this steel member data, then I don't get all these errors of buckling of my compression elements that are obscuring my view. And because of that, I will keep that data on these elements, and all the other data I will remove. So I just wanted to, in fact, how do I say it, to give you an idea of what happens when we have section checks that are fulfilling and what happens when we run also the stability checks on top of that. So now the structure is optimized based on section checks that we remember, and also the bracings are set to only be checked for section checks. So I will also remove this element, and then we have our structure. I will hide the labels because I don't need them anymore. And then we will proceed to explanation of buckling settings. So now when we would run this these checks, we will see that we will have lots of problems with the stability checks. And that means that we should go and check whether our buckling lengths are defined correctly. So normally buckling settings are listed in this dialog, but at the moment I don't have any settings defined. So the best way to define these is if you select the 1D member and then you go to the buckling group. So here you will see there's this property and there are these 3 dots, and when you click on them you see another setting, another window. It's in fact a 3D window which shows you certain things. So first of all, it shows you graphically what are the spans of this member. So you can draw the member, for example, in parts. You can draw it as one continuous member. It doesn't matter. SCIA detects that this is, let's say, a continuous member over multiple spans and tells you in your strong axis direction, we have detected that you have some buckling supports here, and that you have also some buckling supports in this direction. For torsional buckling, we will assume the same supports apply as for the weak axis direction supports and for LTB as well. And also here you can define some additional settings for your SLS checks, so the spans for which the SLS should be checked, and also the limits for the deformation. So in fact, here this first group is defining our spans, and the second group here is defining some important settings, like is this member in a sway frame or a non-sway frame, and what is the buckling factor. And these are the, let's say, 2 most important settings you will find in this dialog. Generally, if you don't have 2D members in the structure, only 1D members, most of the time these settings are quite correct. SCIA detects, I would say even in 100% of cases, if your structure is well connected, there will always be a correct assignment of your, let's say, buckling supports. And so here you can go and say, this is column middle, you can define some name for it, and then you save it. And then the nice thing about it is that now these settings can be applied to many members at the same time. So if I now apply it to these members, when I go in this dialog, I will see all of the members that share the same settings. I am not going to spend a lot of time on that, so I will directly open a model where I have defined the buckling settings already. So you can imagine that if you have a corner column, it is supported in more directions than in this column, and so a separate setting should be defined for this type of columns. And so I've done that exercise already. And if we go to the steel menu and we go to the library of buckling groups, here we can go and see all of the buckling groups that I have in the model. So here we have this type, and then we have also, for example, for the rafter. Now for the rafter, what I have done, something important to keep in mind. So by default, SCIA detects that this is the strong axis and this is the weak axis supports given by the purlins. For LTB, if you have a relatively high section, generally SCIA will assume that LTB is also supported in these locations. But what I have done is, here you can see it, I've disabled these supports. I've disabled them, assuming that there is no LTB restraint on this level. And then I have gone separately in this item here called LTB restraints. And I have defined LTB restraints on my member. So here you will see these little, let's say, tags. These are the LTB restraints, and I have defined them on all my rafters. Not on these ones because they are quite a small section, but let's say here I've said on the top side, this is how it looks like if it would be the bottom side. On the top side, I have a support against LTB, and on the bottom side, my flange is free to buckle. So this is the, let's say, the buckling settings explained quickly. I will again look in my cheat sheet to see if I have missed something. Of course, I didn't say anything about the sway and non-sway setting. We've just used, here you will see from setup, and in the setup it is defined that the strong axis of every column is assumed, or column or beam is assumed to be sway, and the weak axis is assumed to be non-sway. Now, this is not really good enough, and for that I go back to my presentation and I will show you the logic of the calculation of buckling factors in SCIA Engineer. So this is from the help of SCIA Engineer, and there it is said for the calculation of buckling ratios, there are some formulas that are used and are explained in the following references. If you have a non-sway structure, this is the formula. If you have a sway structure, this is the formula. So in fact, if you sometimes see strange buckling factors, it may be because your sway or non-sway setting is wrong. So here I've shown just a random function, but I want to explain the logic of it. So here imagine that you have something which is described by two formulas in two different ranges. So if you are now in this range and you still would like to use this formula, then you will get the value here, which is different than the value here. So I've noticed a lot, if you have a non-sway frame and you set it to sway, it gives sometimes very high buckling factors, and that may be the reason why you're getting the high buckling factors. That's one thing. And the other thing is also from the help, the used approach gives good results for frame structures with perpendicular, rigid or semi-rigid beam connections. So it means that every time we have a hinge, we need to check the buckling ratios, whether they make sense. In fact, this is derived for multi-story frames which are rigid or semi-rigid, and because of that, the hinge case is not always very well taken into account. So in fact, in order to know whether to set sway or non-sway for our structure, we need to run stability analysis. And but first, before you do that, I would really advise you to do something else. And that is to go inside the steel setup and set everything to non-sway. And what we will do now, the whole idea of this is that we would like to obtain sections that make sense a little bit, because if we do not do that, we will run stability analysis and we will get very low factors. And then we will then go to the buckling settings, we will set everything up, then we will run the checks, and then we will obtain bigger sections. And then we will say, yeah, why did we put these large buckling lengths? Let's run stability analysis again. And then we will iterate, and it will take us really a lot of time. So what we will do now is we will set the whole structure to non-sway, and then we will go and run the AutoDesign. And AutoDesign, in this case, I will run the same AutoDesign I showed you with the section checks. In fact, it does exactly the same thing, but I will run it in a batch. And that I do via this menu calculation, AutoDesign, and here I find my AutoDesign that I want to apply. It's this one. And then it asks me, do you want to do it for all the sections or some of them? I will do it for all the sections. And then, in fact, here there are different options. In fact, I can run AutoDesign, or I can even run AutoDesign and then do calculation automatically and then AutoDesign again if I want to iterate. But in this case, I will just run the AutoDesign without a recalculation. I will recalculate manually because I think it is good enough for this structure. So now what SCIA is doing is it's going in here, you will see all the different sections at the bottom, and it is changing them, and then for all of them it obtains I think here I forgot to change something. So here in my AutoDesign parameter, I made a small mistake. So I will reopen this. I think here, because of the type of section, I can only change this parameter. And so, in fact, I can run it again. Okay, project not calculated. Okay, but you get my point. So in fact, my haunch was not optimized because I didn't set to change the cross section. So in fact, in this way, you see that we have obtained bigger sections, and these sections are good enough for the case where my structure has not, let's say, not large sway deformation. So more or less these nodes here remain in their place, and these sections for that situation, they are good enough. And then in this moment, so I can just go and now and show you. In fact, it's only this section that I didn't optimize, so here I will get the problem. But all the other sections are okay. And imagine that I had also optimized this one. I can go now in the calculation and just set up the stability analysis. So I think normally if we go here in the settings of these are mesh settings, in the stability analysis settings, we can select type of solver and also how many buckling modes we need. So in fact, I have already prepared a model with the stability analysis results ready. And there I have defined, I think, 5 different stability combinations. And each of them I have calculated with 75 modes. And the reason is because we have so many elements buckling at a very low load, like the braces, we have many modes. And so here I will show you, I have used these, again, auto-generated combinations in the same way we generated the nonlinear ones. I have the following combinations with wind and snow. And then I have calculated these with 75 modes. I will show you here maybe in the calculation settings. I have here 75 buckling modes. So if we go to the results, usually what we expect to see is here we have very, let's say, many local modes, and these are the diagonals that are buckling. And I think that this is the most time-consuming and nerve-consuming aspect of doing the so-called Plan C design of a steel structure using linear analysis. That the fact that we have to go through all of these modes and determine which ones are in fact sway modes. And in my presentation, I had some examples. So here you see what are local modes and what are global modes. So here you see this is certainly a local mode. It appears at very low load, and this is okay because this member is supposed to buckle and it's not supposed to take any compression force. But they also appear, these local modes, at high loads, because we also have higher, let's say, more sinusoidal functions here. Now, if we look at this shape, this is also a local mode because all of the nodes are not moving and just these 2 members are buckling at the same time. This is also a local mode. If we look at this one here, you may say, yeah, this is a global mode. When in fact, if we look at how the structure is located, we see that again, the nodes are not displacing. Maybe only here for this element, but this is just a secondary element, and it doesn't really care about such a deformation. Maybe here we can disable the buckling support in this case, but this is not a sway mode. In fact, a sway mode is something like this, where we see that the nodes of our structure are moving. And this happened, I think I have it here on my cheat sheet for this model. We have the combination with the index 2, and then the mode number 27. So it is this one. And what we see is that we have some movement of the structure at a very low load. In fact, alpha critical of 3.43. Then another example of a mode is here number 35. Number 35 is this one. And so we see that we have a problem with our structure, and I will tell you why this is a problem. Because for one reason is that if this structure was moving in the other direction, we have rigid connections, and we can just tell SCIA, well, calculate the factor based on the formula for the sway mode, and then we are done. Then we don't have to do anything. But in this case, we have hinges, and then the calculated factors will also not be okay. And the other problem with this structure is that normally we know from basic design that we have the strong direction of our structure and the weak direction of our, so this is the strong direction of our structure, the long one, and this is the weak direction of our structure. This is normally how a steel hull behaves. We see that the strong direction of our structure is somehow not very strong. So in fact, stability analysis is not just there to tell you, well, you have to use another setting. It's also there to tell you that maybe your structure is not very well braced. And so what I've done, what the first reflex I had to solve this is to add some bracing here where the displacements are large. I think that if I would add a brace here in this field, I think that this deformation will be killed once and for all. But let's say that I don't have the possibility to do that. So what I've done is I've added, let's restore the extrusion of the member. So here I've added these bracing. And this is, of course, they are really small. Maybe they're not so efficient. This is for the purpose of trying to get rid of that deformability of the structure. And this is why stability analysis is also helpful to tell us how we can improve our structure without having to improve and use very big sections for the members. And so here I had some other modes that I wanted to show you. What was the effect of adding this bracing on the structure? So first of all, that mode that you saw at critical load factor 3 completely disappeared. And in fact, if we go now, it is, now the indexes are different, but more or less the logic is the same. So here, number 53 at around 6, we also get some mode, which is in fact, with a little bit of imagination, we can completely not see that it's displacing in this direction and say this is a local mode for this column. So this is good. So it means that in fact we managed to stop this deformability of the structure by adding these braces. But the bad news is that in fact there was one mode, and I think that this is in this one, and it was the last mode before 10. It's this one, which says, well, your structure is still too flexible in this direction. And so in fact it means, yeah, certain elements, and these are in fact these columns here, and these columns in this direction, in the weak direction, and these columns here, I will show it like this, in this direction, so the facade columns in their weak direction, they are displacing. They are sway. This is a sway frame, and you need to use buckling lengths that are bigger than 1. But for the weak axis, I have hinges, so I cannot use SCIA's calculation. But what I can still use is the so-called buckling from stability analysis. So if we go to the menu steel, we will see there when we have stability analysis results available, we see this stability member data. Here I've used a little bit of a trick to show you the modes better, so I will turn it off. In fact, if I go to the color settings, I will restore the default so that we can see the structure better. So this stability member data, what it does is you can just select the mode for which you want your buckling factor to be calculated. And I have it in my presentation. I think, let me see where it is. I think it's this one. Oh no, it is this one. So in fact, it's a quite straightforward calculation. And what we can do is we say for a certain buckling mode that we know that the certain members are buckling, use that factor, that critical factor, and the internal force in that member to calculate the buckling factor. And in fact, this is applicable to any structure, and it's not limited to whether you have hinges in your model or not. And so, so in fact, here I can find this evil mode. It was this one. And I can use it to calculate my buckling factors. There are two pitfalls of this method, and one of them is the fact that it asks you for both directions at the same time. And this can be quite problematic because now I want to use this mode for the kz factor, but I know that my ky factor is below 1. And in order to obtain that, I need to, instead of 75 modes, maybe evaluate 150 modes and derive a buckling mode where this member is buckling. And this, I will show you how to go about that and how we can go away from that limitation of the software. So let's say I have an example project where I think I've already inputted them. I'm sorry, attributes. Yes, I have already inputted that stability member data. And so what I've done is I've used the same, I think here I've used the random mode, in fact, something with a higher factor. And for the KZ, I have used the mode in question. And so as soon as you have this mode here, you're able to see the buckling factors in two ways. Here by the member data of the stability member data. So here you will see immediately your K factors. And also in another way, let's say we just go to steel slenderness. As soon as you have these data labels activated, you can immediately go and see your factors directly in the result service steel slenderness. And of course, here it's like just too many values, but I will disable that. So here I want to see local extreme. And also another, I will show you also another nice way to just select the members who have this. So let's say I want to work only with the members which had problems with the buckling. And I will go here. Now the stability member data is there. If I now, when the member is selected, select let's say the members with the same property, I'm able to isolate them for the rest of the structure, for the ones that don't know this trick. So in fact, now I have the stability factors, but they are only, let's say, usable in one direction only. Another thing that I find is a problem when you are using stability analysis is that here, if you go to the buckling settings, what I've done is I have disabled the buckling support in this direction. I saw during the stability analysis that this is displacing as like one member. And if I would activate this support here and I obtain a shape which is not affine to my deformation, then when we look at the results, I get this little bit weird in the short areas of the columns, I get these really high factors. Most of the time, they are not a problem because the length is really small and probably the check will not explode. But if you have a problem with this, what helps is to just go here and disable that buckling support so that the member is treated as one entity that is buckling. And then for that one entity from stability analysis, the buckling factor is derived, and then you will see that we don't have this problem anymore. Usually this problem doesn't happen if you have a buckling shape which is in fact supported by these lateral restraints. And so the first pitfall of this method is that it's asking me about the KY factors, and I at this moment don't have even the buckling shapes to assign to it so that it correctly will determine them. And you will see here 1.7 instead of 1, what I would expect, or something less than 1. The other pitfall is that every time you need to run analysis, you need to calculate your 75 times 4 or how many buckling stability combinations you have every time you want to recalculate the model, because if you don't have these results, then you get an error in the check. So what I would advise you is, as soon as you know your factors, just copy them to your buckling settings. And this is what I've done in this model here. And I think that this is the best way to counteract both of these problems with the functionality. So on one hand, we don't have to always calculate stability analysis, and on the other hand, we it's simply easier to manage the model. So what I've done here is I've gone to the buckling settings of all of these entities, and I have simply introduced the factor. So here for the Y direction, I want to have it calculated. For the Z direction, I just use the one that's the stability analysis provided to me. And I've done that. I will show you also here for maybe this one I can show you. I think it was the one that had the biggest problems. So here for the Y direction, I use whatever SCIA calculates. And for this direction, I use the 115 given by the software from the stability analysis. So now when I have introduced them in the buckling settings, these factors, I don't need these labels anymore. I can just grab them and delete them, and hopefully I will not need them ever again. And so in fact, now at this moment, I will just activate just the structure. I will disable the labels of the buckling settings, this setting. And now finally, I can run my structure and I know that all my buckling settings are correct. And I can optimize, I can run the AutoDesign from here, or I can run it from the overall AutoDesign. And that will be more or less my final sections. I think I had one slide related to that. Don't forget to run your nonlinear combinations with tension only, because after with the correct settings, I optimize the structure. If I use linear analysis results without tension only, this is what happens when I run the same checks with tension only. So don't forget to keep that in mind. And I think these were the most important things that I want to show you today. In fact, all of these slides, I made them for the ones of you who would be interested to share it with your colleagues. So feel free to contact me, or just write in the chat window that you would like to receive the presentation and the model, and I can send them to you. This is my email address. I think I'm already 15 minutes late, so I will not have time to show you SLS as well. I think now I will go and start answering your questions, which I think my colleague has been doing the whole time. And also do not forget to tell me if you have any other ideas about the second part of the webinar, what topics you would like to see. Of course, if it is connections or something like this, we will probably put it in another webinar, because it's going to be too difficult to manage everything within 1 hour. But in the next session of the webinar, we will do second order analysis with initial imperfections, and I will show you the SLS. But if there's anything else, you can be brave, and you can even send me your model, and we can discuss it together at the next webinar. There is a function, the question, how does the result log function work? We'll again share my screen. So the result log, so what it does, let me hide this, is, let's say that you have calculated the model. if you click on this function here, it stores your results, but it puts labels on everything that could be labeled. So in the 3D window, you will get this locking of results has been switched on. And in fact, it lets you do many things. You can just go and delete a column, for example. You can go and change. The biggest benefit of the result lock is that you can change the cross sections. So for example, if I go here and I run my check for, just as an example, on just this member, and then I go to the member properties and I switch it to something smaller like this, and I run the check again, it will fail. So that's the biggest benefit of the result locking, is that you can check what's happening in your structure if you do some small changes, assuming that the results didn't change a lot. Of course, in the end, if you now go to the engineering report, you will see red labels all over, result locking on. In the end, you always have to recalculate your results, but sometimes it is useful to be able to store them for a little bit longer, so that you can do some things and not have to recalculate all the time. Especially if you decide that you will um, always work with nonlinear results and so on, then always do second order analysis with imperfections, and it's always good to use result locking. So the recorded webinar will be added on YouTube very soon by our marketing team. Can we have cold form purlins in SCIA Engineer? Yes, of course. I will be giving a webinar in September on design of cold form steel. We are, let's say, very advanced in that functionality. We do classification, we do effective section derivation, also general shapes we can handle. But certainly cold form steel is something that without a problem can be managed in SCIA Engineer. Is it possible to use the 3D wind generator on circular structures? Not according to the Eurocode, not the 3D wind load generator, but a colleague of mine published a webinar where he in fact showed a plugin that he has created. I think it's on SCIA Garage, where you can just via Excel copy paste the load on a reservoir from Excel to SCIA Engineer, and it works quite well. Is it possible to define an exclusive load case between standard snow and snow accumulation? Yes, certainly yes. That's not a problem. Why 75 modes and not 100? It is simply because I try to achieve factors bigger than 10. If your structure requires it, or if it needs less modes, you can probably pass with less. As long as you pass the mark of 10, I think it is fine. Somebody asked me to show my email again. So thank you for attending the webinar. I will look at the last questions, and then I will send the recording to our marketing team so that they can add it to our YouTube channel. And then I will contact the ones who wanted to receive a copy of the presentation and the model. There is a nice question about after we have optimized the structure, do we need to change the buckling lengths again? I don't think so. If you are always changing the sections to bigger ones and you've run the stability analysis with, let's say, smaller sections, and then you have bigger sections in the last design, then I don't think that you should update the buckling settings unless you think that your section is much bigger now and you maybe get a more economical design. But for other reasons, I would not do that. Thank you everybody for joining this webinar. I will stop the broadcasting now, and thank you again for showing up today.